Donc, je vous demanderai de vous installer, s'il vous plaît. On démarre. Merci. J'ai l'impression d'être en cours. Bon, bon, pour cette dernière session, donc, l'axe OPA, donc ordonnancement et planification du GDR de recherche opérationnelle, a le plaisir d'inviter Federico Della Croce, qui est un collègue professeur à la Politecnico de Turin, et donc qui va nous parler de le LPT revisité pour le problème AM machine et CMAX. Merci.
Bonjour tout le monde. Je remercie ROADEF et celle de CNRS pour cette invitation. Ceci dit, je vais swapper à l'anglais, sur lequel je suis un peu plus à l'aise vis-à-vis de l'aspect scientifique. So we're talking about parallel machine scheduling. This is a joint work with Rosario Scatamacchia, who also works at Politecnico of Torino. The outline of the presentation, let me keep this just to have an idea on the timing. Here we're going to talk about approximation and actually linear programming. When I was requested to do this tutorial, I was thinking to what to talk about, and I thought that this work was kind of interesting. I had fun in working on that. It was a very known result. The result was by Graham, was in the around the 60s, so about 50 years ago. And the fact of using linear programming within approximation, there is a standard way for doing it. We will go over that, but then in this case, it was nice to have a kind of a slightly different way of using linear programming within approximation. So we will start with a gentle introduction on approximation and linear programming, and then we will talk about the problem, which is the minimization of the make span on parallel machines. So we'll talk about the famous LPT rule. And then we see how it's possible to get an improvement on the LPT rule with the same complexity. And then the other part, which was fun in a sense, was the fact of saying that from approximation, sometimes you can also consider heuristics. So the fact of having a worst case result does not imply that you're not going to have something that may be used in practice. And so we show how to find out again a rule which has a very low complexity, and this rule it can be seen as an improvement with respect to LPT also in practice, and some conclusions. So, well, generally speaking, when we talk about linear programming, you know that every course on operations research at some point will deal about modeling. So here again, we're going to talk about modeling, but it's in a slightly different way. And when we talk about modeling, well, of course, probably in the 60s, well, modeling, generating a linear programming model was concerned to the fact of representing a problem, not much of solving it. And then from time to time, things improved, and indeed, at some point, it was possible to solve problems by means of MIP solvers. But this typically works, sometimes doesn't, because problems are difficult. And in the world of scheduling, this is even more true, because there are some problems that can be dealt with by means of linear programming, but there are some other problems. Imagine just the job subset with CMAX as an objective function, or any objective function, that is pretty difficult. You can model it, but then the model typically doesn't work that well. But we have math heuristics, so we can consider the fact of using, we generate a linear programming formulation, so even for problems which are difficult, then if you think of math heuristics, so you can imagine using these sort of macro local searches, search approaches, in which in between there is embedded the solution of several easier problems, because there are very few variables within, and so those problems are solved to optimality, etc., etc. And generally speaking, with respect to approximation, it is quite standard whenever it is possible to To represent the problem, I mean linear programming formulation, an integer linear programming formulation. Then by solving the continuous formulation, which is something we like because we know that it corresponds to can be done in polynomial time. And with some kind of rounding, we can manage to get to obtain some approximation results. So let us move to the world of approximation. We focus on the fact, maybe I can do that, which is better, at least for me. So in the standard world of approximation, if we denote by opt the optimal solution value, and let's say that we have any algorithm, and we say that A, as acronym for algorithm, the solution value of the approximation algorithm, then we're looking for the performance ratio, which is the ratio A divided by opt. And of course, in approximation theory, we're interested in the worst case approximation ratio. So whatever instance you're going to do, have what will be the worst ratio A divided by opt. And generally speaking, even though in the recent past there is quite a bit of work in approximation results with moderately exponential algorithm, we are interested in polynomial time complexity. So as an example, imagine you have these two graphs, so the graphs on the left and the graphs on the right. In the minimum vertex cover, we want to cover all edges of the graphs by selecting some of the vertices. So if you go on the left, you see there is in this case the vertex cover is given by the red vertices. So on top we have a solution in which we are using 3 vertices. On below we have a solution have just 2 vertices. So the solution below is better than the solution on top. Same thing is on the right graph. So in the vertex cover is a selection of the vertices of the graph so that all edges have one of the 2 extremities which is in the vertex cover. So if you look at every edge here for all solutions, there is at least one of the extremities which is red, basically. And this problem has a well-known approximation ratio which is equal to 2. There are different ways. Actually, there are also pure combinatorial algorithms, which are faster in a sense that they reach the same approximation ratio. But here we are interested in talking about what I mean with standard ELP model, approximation via standard linear programming formulation. That is, we generate the corresponding linear programming model. So in this case, we define a set of variables xi corresponding to vertex vi, or for every vertex I, we have a variable xi, which is a binary variable. And so we want to minimize the sum of these xi's. But the constraints we have is that for every edge, so for every edge ij, either vertex I or vertex j is in the solution. That's with binary variables correspond to the fact of saying xi plus xj is greater or equal than 1. So given this formulation in polynomial time, we can compute the optimal solution of the continuous relaxation. So we have this problem there in which we just say that the xi are between 0 and 1. And by solving to optimality this problem, and then by doing something further, which is some rounding, in this case, the rounding is set all variables which are greater or equal than 0.5 to 1, and all the other variables will be equal to 0, then we have a feasible solution. And this solution, as we have at most doubled the values of the variables, is not, the value of the solution is not more than twice the continuous relaxation. So of course we have an approximation ratio which is equal to 2. So what we do here, we have a problem, we formulate as a linear programming formulation, we have the continuous relaxation, we do some rounding, and we get our approximation result. I mean, this is an easy one, let's say, but actually there is nothing better than that in literature. But in this case, in this presentation, I want to talk to you about what I call non-standard ELP model approximation. So in non-standard ELP modeling for approximation, the issue here is the fact of saying, why don't we try to mimic? So we're still modeling. Why don't we try to mimic by a linear programming formulation, not the problem, but the behavior of the procedure that solves the problem. In this case, a greedy procedure. And that's why, in this case, it worked well, the fact of talking about the PC-max problem, so the problem of minimizing the makespan, the Cmax on a set of identical parallel machines, because there exists the longest processing time rule, which is well known, well used in practice, and that has a given provided approximation ratio. So let us see what is the problem. You see, we have a bunch of jobs. Let us see the picture, the picture below, and I hope you can see. Yeah, you should be. Yeah, you should see the cursor. And so we have a set of jobs. Let's say we have 3 blue jobs, 3 green jobs, and the black job. And the idea, imagine in this case that we have 3 machines. The goal would be to balance as much as possible all the jobs on the machine, so that basically every machine completes at the same time. This is the best we could do if this is possible. So the longest processing time rule is very simple, just says sort the jobs in decreasing order, or to be more precise, in non-ascending order, and then place the jobs, assign 1 job at a time on the machine whose load is smallest so far. So what we do here, we start with the blue jobs. As you see, they are decreasing, going from top to bottom, the blue jobs. The gray jobs are decreasing from bottom to top. And then there is the black job, which is the smallest job. And what we do basically is that we place the first blue job, then the second blue job, and then third blue job on the 3 machines, whatever is the order, we don't care. But then when we have to start with the first gray job, we assign it to the machine whose load is smallest so far, so the machine which is below, etc., etc. There are a bunch of information. There has been a bunch of results on that. So the LPT rule is very simple. The complexity is nice, let's say. So it's the algorithm is very fast. And let us see what do we have. There will be some notation. At some point, you will be possibly killed by the notations and definitions, but I'll try to focus you on what we're looking for. We're looking for a way of representing the greedy algorithm, which is given by the LPT rule. So assume the jobs are indexed. Let me check those again. Assume the jobs are indexed in decreasing order, or let's say non-increasing order. So from now on, P1 is greater or equal than P2, etc., up to Pn. And let the note by CLPT and C star, actually CMLPT, CM star, the solution given, so the makespan, the value of the makespan of the given by the LPT rule, and the value of this makespan given by the optimal solution. Then we are looking for the performance ratio, so the ratio CLPT divided by C star. But actually, there are a bunch of results that says that we're interested in what we call RK, which is the ratio we get if the value of LPT is given on a machine in which the number of jobs which are assigned to the machines is exactly K. So if we have a solution like in the picture below before, in which there were 3 jobs on the machine that was providing the makespan, we would talk about R3. Okay. So generally speaking, we are interested in whenever we analyze LPT, in what happens to the critical machine. The critical machine is the one that provides the makespan, and which is the critical job. So the critical job is the last job on the machine that provides the makespan, which is actually the smallest job on the machine that provides the makespan. In our example here, the critical machine is the second one, and the critical job is the black job. So we have a bunch of results. Recall we're talking about greedy algorithms. So for us, the issue here is that we have information. Those are requirements. Those are, in a sense, constraints of our linear programming formulation, whatever we are looking for. So these are results provided by the literature. For us, they will be constraints. So for instance, here we know that the optimal solution is not inferior to the largest processing time job. So we know that CM star will be greater or equal than P1. Similarly, the optimal solution will be greater or equal than the sum of Pj divided by M. These are information, these are inequalities. And we know, I mean, we actually know that if the critical jobs, which typically is the smallest, the last job which is placed by LPT, generally speaking, if Pj prime, and J prime is the critical job, is larger than C star divided by 3, then we know, I mean, the results have, we have information from the past, from the literature, that then the solution is optimal. So this implies that in our formulation, if LPT is not optimal, we can assume that Pj prime is smaller or equal than Cm star divided by 3. This is another inequality. Okay, this is the kind of things we are saying. Grams in 69 provided the approximation ratio by showing that, let me go smooth here, that LPT actually has this value of the approximation ratio. And our goal is to see if we can improve it somehow by working on it. And there are another information which is provided again, another inequalities, is that for a given job I, which is assigned by LPT to position J on a given machine, that we know that Pi is more or equal than the optimal solution divided by J. Again, another inequality. I mean, I know there is too much of notation, but the issue is just to say there are a bunch of requirements which are actually all linear inequalities, can be seen as linear inequalities. So we have a bunch of, now the analysis of the problem and of the results we have. What we actually know is that the approximation ratio by Gram is obtained when actually the critical job is the third job of a given machine, in the sense that if LPT places, I mean, finds a make span and the critical job is either in second position or in first position or in position K larger than 3, then we get approximation results which are provided by I mean, different papers in the past that are large, that, sorry for this, whoops, okay. All these results are slightly better. So our goal is to, what is written here below in blue, the fact that if we manage to improve R3, then we improve LPT. So to find the better solution for LPT, we just need to focus on instances where the critical job is in position 3, okay? And indeed, all typed worst case examples are of this type. So if you have 2 machines, then you're gonna have 2 jobs with processing time 3 and 3 jobs with processing time 2. If you have 3 machines, you're gonna have 2 jobs with processing time 5, 2 jobs with processing time 4, and 3 jobs with processing time 3. And generally speaking, with n machines and 2 n+1 jobs, all solutions will be, I mean, all worst case solution will be 2n-1, 2n-1 for the first 2 jobs, 2n-2, 2n-2 for the second 2 jobs, etc., etc., etc. And eventually, at the very end, we have 3 elements, three jobs with processing time m. So if you look at the problem with 2 machines, it's quite clear that LPT will place the first 2 jobs on one machine and the other, the second 2 jobs on one machine and the other, and then there is that's Italian, you see, I'm Italian, so I need to make some fuss on that. The last job, which is in there and says what kind of a machine, and the solution value is 7, while the optimal solution is 6, okay? So the worst case for 3 machines is the same, then you get 11/9, and generally speaking, you get 4m-1 divided by 3m, which corresponds to 4/3 minus 1 divided by 3m. So the worst case always occurs, by the way, when n is equal to 2n+1, so it's a small probe. We have m machines and just basically a couple of jobs on any machines plus 1 job. And this last job is the one that provides problems or provides our worst case instance. And not only this, but the other information we have is the optimal solution is actually given by the sum of the processing time divided by m, which is one of the best lower bound we have. So the best balancing we may assume. So we really are unlucky to be in that situation. And so we will focus somehow on that situation. So what we need to do is to find out a way for handling things. What we can say, by the way, is that, first of all, for the time being, at least for the presentation, we will focus on the fact that J prime is equal to n, so it's the last job, is the smallest processing time job. But I mean, this is not a strong generalization. And the other thing is that if n is smaller or equal than 2m, or n is larger, greater or equal than 3m plus 1, basically, we have results that provides us the information that we managed to get an improved result with respect to LPT. I mean, with the worst case ratio of Graham. So actually, we need to analyze for n greater or equal than 3 in the sense that the case with m equal to 2, which is actually the partition problem, we leave it away, and then we'll see what happens in that at the very end. And so this implies that either n is between 2m plus 2 and 3m, or we are in the real worst case for LPT, which is n equal to 2m plus 1. And for handling these cases, we apply linear programming in the way you will see in a minute. And also we do some branching. So the issue is, how do we handle all the possible subcases? Well, we know what is a branch, and in our case, we're going to branch the possible options. Of course, we need to not to have billions of options for a bunch of reasons. Among the others, the fact that it will use too much time. The second thing, that no one will publish a paper with 2,000 pages or so. So now I'm showing you one example. Possibly I won't be able to show you a second example, but at least the first example I would like to make you understand how it works, and I hope it will be quite easy to understand. So the case is the following. We have n, which is between 2m plus 2 and 3m. So this implies that, roughly speaking, we have generally 2 jobs on every machine, and then at least a couple of 2 jobs on each machine, and at least 2 machines that have 3 jobs. And why so? Because if the critical job is in position 2, we already have an improvement, so we have to consider the case in which the critical job is in position 3. And indeed, there is some other job that must be placed somewhere. So there will be at least another job, as it is mentioned here, in position 3. So we consider an LP model where we arbitrarily set the value of the optimal solution equal to 1. So this will be our variable, opt equal to 1. And where we want to minimize the value of CM star. Pay attention, we're talking about M. M is the number of machines, so it can be any. So we have to deal with this case. But generally speaking, in terms of research, when we were doing that, we started using M equal to 4, 5, 6. So M was a constant. And then eventually, by duality, we managed to handle that. So we have a CM star, the optimal solution, and this will be what we're going to minimize. Let's say that there is some given starting time of job n, and so let's denote by capital L the starting time of the critical job, so that the value of the completion time of LPT is given by L plus the processing time of the critical job. Let's introduce 2 further variables. C1, that is the completion time of the non-critical machine, which has at least 3 jobs. With C2, the sum of all the other completion times, so the completion time of all the other machines. So we have the critical machine, we have this machine whose completion time is C1, and then C2 is all the other completion times. And of course, this value C2 correspond to this equality, the sum of the processing time minus the completion time of this second machine with 3 jobs, minus the completion time of the critical machine. And then we have some other constraints that we can use. One says that due to list scheduling, LPT uses list scheduling. So we always place the jobs in in the machine available who has the smallest load so far. So this implies that we know that LPT will respect this constraint, which is C2 divided by n minus 2 is greater or equal than n. And eventually, as we know that job n is in position 3, we know that the processing time of this job n cannot be superior to Cm star, the optimal solution, divided by 3. Okay, which basically says that the optimal solution is at least 3 times the smallest processing time, which is always a condition that holds. And then we have a linear programming formulation. Notice this linear programming formulation actually has 7 variables or something like this, so it's very small. The only issue is that this is, for the time being, this is not a linear programming formulation, because we have these variables. So we associate variables Pn, sum P, and so Pn is the processing time of the smallest processing time job, sum P is the sum of the processing time, and then the variables C1, C2L, and opt that correspond to capital C1, capital C2, capital L, and Cm star. And so we want to minimize opt, but we're going to say that the sum of the processing time divided by m must be greater or equal, must be smaller or equal than the optimal solution. So the optimal solution is at least equal to the sum of processing time divided by m. We say that C1 must be greater or equal than 3Pn. We say that C1 must be greater or equal than L. We say that actually C2 must be greater or equal than m minus 2 times L. All these are the constraints, and so on and so forth. All these constraints are derived by the requirements, actually the constraint provided by LPT and the least scheduling, etc., etc. If we do this, we can find the optimal solution for m equal to, say, 4, 5, actually to 5, because this is related to m greater or equal than 5, for m equal to 5, 6, 7, and eventually by a little bit of reverse engineering, we managed to see that actually the Lewis solution, the primal solution, and the Lewis solution were coincident for these values of so we were able to show that by having Pn equal to n minus 1 divided by 4n minus 5, etc., all these values of Pn, C1, L, sum P, C2, etc., we have a solution such that for every m, the primal solution and the dual solution coincide. And so, of course, this is correspond to the fact that this is the best we can do. And if we do that, actually what happens is that the optimal solution has the value 3 times m minus 1 divided by 4m minus 5. And if you reverse this value, this corresponds to 4 over 3 minus 1 divided by 3 times m minus 1, which is indeed better than 4 over 3 minus 1 divided by 3m. So in this case, we are just ruling out the possibility of having a worst case corresponding to the worst case by Gram when n is in between 2n plus 2 and 3n. So now we are happy because we are getting closer, because now we really have to deal just with the case where n is equal to 2n plus 1. So indeed, what happened is that by the same kind of reasoning, we were able to handle this result when n was between 3 and 4. We were able to show that for n smaller or equal than 2n and m greater or equal than 3, the value of LPT was inferior to this value here. So basically, the only result we were dealing with was this one. The only case remaining was where n was equal to 2n plus 1, and where LPT schedules just job n in third position, and n is critical, which is a kind of peculiar situation. So now we have to do something, but the problem is very specific. We have exactly 2n plus 1 jobs, and the last job will be in third position, and basically the first 2n jobs will play the game of going from the first machine to the last machine. So we have job the first job on machine 1, the second job on machine 2, etc., etc. Then we go back like this, and we arrive to to job 2m again on machine 1. And then there is this last job. This is the situation of LPT. This is the worst case that I showed you before. Okay. So in this case, we say, okay, let us do something. And indeed, it is sufficient to try to use a very slight modification of LPT, which is the following. The modification is as follows. You run LPT and you get your solution. And also, you take out the smallest processing time job, you put it on a machine, and then you apply LPT. And that's it. Okay? So formally speaking, we consider the variant LPT of S, where capital S represents the set of jobs assigned altogether to a machine first. And what we do is, we do it the smallest job. We do it with the critical job. But I was saying you that for the time we were considering J prime equal to N. So we take this job, we put it on the first machine, and then we apply LPT. So the complexity is the same. Actually, we run basically twice the same algorithm. And what happens is that we can show, but I'm not going to do that because I'm not going to have the time, but I will at least tell you something about it. We managed to show that it is possible to improve. The issue is the following. So we have a bunch of subcases. We need to consider the fact of what is exactly the value n. N is indeed equal to n plus 1. So this is the subcase we are considering. Then the processing time of the smallest job can be either larger than or equal to the processing time of the first job minus the processing time of the nth job, or it is smaller. And then we have to consider another case. So the other cases in which we have the critical job, but the job I, which is critical in LPT prime, the second round of LPT after having placed the critical job on machine 1 is different, etc., etc. But if what happens in all these cases, we have additional information. You see, the first information, when I was considering the blue ones that we were considering, which are actually the cases that provides the worst case, are there is another information. So we know that P2n plus 1 must be greater or equal than P1 minus PM. So again, this is an information that we can provide. And so we keep on going this way. And what we know, and I'm going quickly here, is that indeed the LPT solution is of this type, but if the LPT solution is of this type, also the LPT prime solution must follow some conditions, some rules, okay? So that's the issue. We can, let's say, induce some further constraints to be added to the linear programming formulation. So, well, let me skip this. The only thing which was important in this case is that we could manage to show that for that very particular case, we were reaching a ratio which was equal to 7/6, which is indeed what we're looking for, which was, it is much better than 4/3 minus 1 divided by 3m, by using a linear programming formulation, where if you look at this formulation, the number of variables is very limited, because actually we need to, well, I'm using here variables x instead of inducing corresponding to processing times, and we're using variable x2m plus 1, xm, x2m, xm minus 1, xm, x1, and opt. So we have 7 variables, whatever the value of m is. So in this case, we don't even need to check whether, what are we going to do with the dual formulation. It's straightforward. And the same kind of reasoning with, I mean, a bunch of different considerations can be done for all the very special cases. So that we managed to get this improvement in terms of worst case complexity. Now, from approximation, we start to say, okay, can we do something in terms of heuristics? So can we do something like this in terms of heuristics? And of course, it was not the fact of saying I have the critical job and I put it on a machine. And indeed, we were analyzing the worst case. And in the worst case, what was going on was that this job here was the jobs that I didn't know where to put it. And so we started saying, okay, but what is the reasoning of LPT is the fact that we are reducing always the processing time, so the error will be not too much. But in the same time, what happens is that typically, like in this example here, we start putting all jobs on one each on a different machine. So the first M job will be on M different machines. And then again, the second M jobs will be on M different machines. And in our worst cases, actually, this was the behavior, generally speaking, of LPT. And so the idea here is the fact of saying, okay, why don't we split the sorted job set in two pools of M consecutive jobs, M, 2M, 3M, etc. And we just check the difference between the largest processing time and the smallest processing time in every tuple. So what we do is the following. We add 0 dummy jobs if necessary. So for 7 jobs, we would add two further 8th and 9th job with process time 0 if we have 3 machines. And for each tuple, we compute the slack P1 minus PM, PM plus 1 minus P2M, P3M plus P2M plus 1 P minus P3M, etc., etc. And then we sort the tuples according to this slack. And then we apply list scheduling. Exactly, it's the same thing. We need to sort the tuples. So in our example here, this corresponds to the fact that for 3 jobs, we're gonna add 0, 0 here. So you see the tuples are 554, 433, 300. This implies that this difference is larger because 3 minus 0 is equal to 3. And then those two have the same value. So in this case, this is the sort we have, and this is the list scheduling that we get. And actually the solution we get is slightly better than LPT. So we tested LPT compared to Slack on instances from the literature, uniform instances and non-uniform instances. I guess it's time for me to speed up, right? And so roughly we have, say, 780 instances. Well, the results indicate that indeed Slack wins over LPT. So complexity is roughly the same, and the number of wins and the number of ties, etc., is you have it about here. There's something wrong maybe in these tables. Let me check. Because if I'm telling you about 780 instances, this is less. But okay, whatever it is, maybe these are the non-uniform instances, and then there are the uniform instances. Okay, that's one. The sum of those. So generally speaking, anyway, Slack is clearly superior to LPT. It requires basically twice the time, something like that, but that's it. And what also we checked was with respect to the literature, and indeed what we managed to obtain is that Slack was indeed sufficiently competitive with the literature and much faster. And applying Slack with a very short step of neighborhood search, just to improve a little bit of solution, using a little of the time saved, we get a better solution, generally speaking. And well, let me go to the conclusions. Well, for the case with m equal to 2, actually we did something different. There was already a result, apart from the fact that there is an FP test for the problem, but in practice there was a solution which was 9/8. By the same kind of approach, we managed to reach 13/12, but was different because it was really typically, that was a special case, so we needed to do something different, but again, using linear programming. And generally speaking, whenever we have constructive algorithms for the solution of a problem, well, it could be worth it to try to use linear programming instead of formal proof systems to get the approximation ratio. And this concludes my presentation. Thank you.
Est-ce que vous avez juste le temps pour une ou deux petites questions?
Oui, c'est bon, ça. Alors, si tu veux, tu pourrais dire que c'est la même de LPT prime, parce que si je parle de Slack tout seul, effectivement, non, parce que je ne fais pas exactement LPT plus LPT prime. Mais je te dirais, OK, je fais LPT prime et je dislike. Non, mais slack en soi-même, non. Le résultat, par exemple, sur les problèmes à 3 machines, on est passé de 11 sur 9 à 10 sur 9, qui est le même de LPT prime. Donc, au point de vue de Pierre, je dirais, ça gagne pas plus que l'autre.
Est-ce que ce type de preuve, de trouver des rapports d'optimisation, ou d'améliorer en donnant sur l'ULP, est-ce que c'est quelque chose qui est vraiment original?
Non, ça existe. Ouais, il n'y a pas, disons, nous, on a travaillé là-dessus. On a travaillé aussi sur le sac à dos incrémentel, à peu près faisant la même chose. Mais j'ai fait une présentation et j'ai parlé avec Yankar Lenstra qui m'a dit qu'il a obtenu un résultat similaire. Nous, dans le papier, ce papier a été apparu sur JOS. On cite un autre exemple, je ne me rappelle plus, mais disons, il y en a pas trop, mais il y en a. C'est la typique situation du style, selon moi, ça vaut le coup de le faire, surtout quand on a des algogloutons, mais il n'y a pas trop, donc il y a vraiment espace pour tout le monde.
On va s'arrêter là. Merci beaucoup.
Merci.